This is the reason nobody has ever traveled up out of the solar system, and why every spacecraft humanity has ever launched has stayed almost perfectly flat instead. Every planet, every asteroid, nearly every comet on a short orbit, all of it moves through space on roughly the same tilted sheet, and leaving that sheet turns out to be one of the hardest, most expensive things you can ask a spacecraft to do. If that sounds strange, stick around, because by the end of this you'll understand exactly why up barely means anything out there, and why the two most distant machines humans have ever built are only just now starting to climb away from that flat plane, after nearly 50 years of trying. Before we get into it, hit like and drop a subscribe. It genuinely helps this channel keep making videos like this one. Start with something simple. Stand outside right now, point your finger straight down at the ground, and that direction feels absolute. It feels like the one fixed truth in the universe, the direction things fall. But it isn't fixed at all. If you extended that same line straight through the planet, out the other side, it would come out pointing up for somebody standing on a boat in the middle of the Indian Ocean. Down for you is up for them. Gravity gives every person standing on Earth their own personal sense of up and down, and that sense only works because you're standing on a sphere with a center of mass pulling you toward it. Take away the planet under your feet, and the whole idea starts to fall apart. That's the trap most people fall into when they try to picture up in space. They imagine some kind of cosmic ceiling, a direction that's up for everybody, everywhere, the same way north is always toward the North Pole, no matter where you're standing on Earth. Space doesn't work that way. There's no floor out there, no ceiling, no absolute vertical. And yet, when you zoom out far enough and look at the solar system as a whole, something strange happens. A direction does start to emerge, not because gravity demands it, but because of how the whole system was built in the first place. Astronomers do have a working definition of up and down when they're talking about the solar system, and it comes from something called the ecliptic. The ecliptic is, in the simplest possible terms, the plane of Earth's orbit around the Sun, stretched outward to include the rest of the planets too. Picture a flat, wide disk with the Sun sitting at the center, and Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all circling around it roughly along that same disk. By convention, if you're floating somewhere above that disk looking down, the planets all appear to move counterclockwise. Flip around to look from below, and the exact same motion looks clockwise instead. Above and below only exist because astronomers agreed to define them that way, using this shared reference plane as the 0 point. The name itself comes from the ancient Greek word for fail to appear, which sounds odd until you learn why. Ancient astronomers named this plane the ecliptic because it's where eclipses happen. A solar eclipse only occurs when the moon crosses directly between Earth and the Sun, and a lunar eclipse only happens when Earth slides directly between the Sun and the Moon. Both of those alignments can only occur when the Moon happens to be sitting on, or very close to, this same flat plane. The Moon's orbit is tilted about 5 degrees off the ecliptic, so most months it just misses, gliding a little above or a little below the line where an eclipse could happen. Only about twice a month, on average, does the Moon actually cross that plane, at points called nodes, and only when that crossing lines up with a new or full moon do you actually get an eclipse. So this whole concept of the plane of the solar system isn't some abstract invention dreamed up by modern astronomers. It comes straight out of watching the sky and noticing, thousands of years ago, that eclipses only ever seem to happen along one particular path. Now here's the part that really answers the why behind all of this. The planets aren't scattered randomly through three-dimensional space. They didn't each pick their own tilted lane and go their own way. Almost all of them sit remarkably close to that same ecliptic plane, and the reason traces back more than 4.5 billion years, to the very birth of the solar system itself. The Sun and everything orbiting it began as a slowly rotating cloud of interstellar gas and dust, cold and diffuse, drifting through space with a very slight spin. At some point, gravity took over, and the cloud started to collapse in on itself. And this is where basic physics takes the wheel and does something almost inevitable. As that cloud shrank, the law of conservation of angular momentum kicked in. the same law that makes a figure skater spin faster the moment she pulls her arms in close to her body. Angular momentum depends on both how fast something is spinning and how far its mass is spread out from the center of rotation. Pull the mass inward, and the spin has to speed up to compensate, because the total amount of spinningness in the system can't just disappear. As the cloud that would become our solar system contracted, it had no choice but to spin faster and faster. A cloud spinning fast enough starts to flatten out, the same way pizza dough flattens into a disc when you spin it. That's exactly what happened here. The collapsing cloud flattened into what astronomers now call a protoplanetary disk, a thin, rotating sheet of gas and dust surrounding the newly forming Sun at its center. That disk is thought to have held less than 1% of the total mass of the young Sun, and yet that thin sliver of material was still more than enough to eventually build every planet, moon, asteroid, and comet in the solar system. Every rocky world, every gas giant, all of it condensed out of that same flattened disk, which is exactly why they all ended up orbiting in roughly the same plane, all spinning the same direction, like pieces of a single flat structure rather than a scattered cloud of independent objects. For a long time, this whole picture was inferred rather than seen, pieced together from the tidy, flat arrangement of our own solar system and worked backward into a theory of how it must have formed. That changed in 2014, when the Atacama Large Millimeter Submillimeter Array, an enormous radio telescope made up of dozens of linked antennas high in the Chilean desert, pointed its full resolving power at a young star called HL Tauri, roughly 450 light-years away in the constellation Taurus. The resulting image stunned astronomers. It showed a protoplanetary disk in astonishing detail, sharper than the Hubble Space Telescope routinely achieves in visible light, and rather than a smooth, featureless sheet of gas and dust, the disk was carved into a series of concentric bright rings, separated by dark gaps, almost like the grooves on a vinyl record. HL Tauri itself is thought to be barely 1,000,000 years old, remarkably young on a stellar timescale, which made the sharpness of those rings genuinely surprising, since nobody expected a disk that young to already show this much internal structure. The leading explanation is that each dark gap marks the orbit of a newly forming planet, still embedded in the disk, sweeping up material and carving a lane clear as it goes, the exact same basic process that once played out around our own infant Sun 4.5 billion years ago. For the first time, astronomers weren't just theorizing about how a flat planetary disk forms. They were looking directly at one happening in real time around another star. It isn't a perfect, mathematically ideal flat sheet, though. There was turbulence in that early disk, enough that the planets didn't all end up locked to precisely 0 degrees relative to each other. Each one has its own small tilt, its own slight lean, away from true flat. Mercury leans the most of the 8 official planets, tilted about 7 degrees from the ecliptic. Venus sits at roughly 3.5 degrees. Earth, by definition, is treated as 0, since the ecliptic is literally defined by Earth's own orbit. Mars leans a little under 2 degrees. Jupiter and Uranus lean the least of all, Jupiter at about 1.33 degrees, and Uranus at less than a single degree, practically dead flat. Saturn sits around 2.5 degrees, and Neptune leans about 1.75 degrees. Pluto, which lost its status as an official planet back in 2006, breaks the pattern dramatically, tilted a full 17 degrees off the ecliptic, which is one of the reasons its orbit always looked a little suspicious compared to the tidy pancake shape everything else follows. Even the Sun itself isn't sitting perfectly perpendicular to this plane, which is a detail worth pausing on. The Sun's own rotational axis is tilted about 7.25 degrees away from a line running straight up out of the ecliptic, meaning the Sun's equator and the ecliptic aren't quite the same plane either. Earth's orbit actually crosses the Sun's equatorial plane twice every year, once around June 4th and again around December 6th, and Earth gets its clearest possible view of the Sun's North Pole around September 7th, the one date when that 7-degree tilt happens to angle most directly toward us. Every other day of the year, Earth is looking at the Sun from somewhere in between, never quite face-on to either pole. Even the Sun rotates unevenly across its own surface, completing one turn in roughly 25 days at its equator but closer to 36 days near its poles, since it's a ball of plasma rather than a rigid body and doesn't have to spin at one uniform rate. Put all of that together, and there's a simple, almost overlooked reason nobody had ever gotten a proper look at the Sun's poles before a mission specifically set out to leave the ecliptic to go find them. Even from the best possible vantage point anywhere within the solar system's flat disk, the Sun's poles are always seen edge-on, at a steep, oblique angle, and never once straight on. The asteroid belt, sitting between Mars and Jupiter, tells a similar story on a smaller scale. Most of the asteroids inside it have inclinations under about 30 degrees, and the distribution actually peaks below 4 degrees, meaning the majority of asteroids hug the ecliptic even more tightly than that headline number suggests. Astronomers who've calculated the belt's own mean plane, averaging out the orbits of hundreds of thousands of catalogued minor planets, put that average tilt at somewhere between about 1 degree and just under 1 degree relative to the ecliptic, essentially confirming that the belt, like the planets, mostly settled flat, but mostly is doing real work in that sentence. A smaller population of asteroids sits at much steeper inclinations, some climbing past 20, 30, even 40 degrees away from the plane, kicked into those tilted orbits by the same kind of gravitational perturbations from Jupiter that shape so much of the belt's structure. So even within a single, well-studied region of the solar system, you get the same layered pattern showing up again in miniature. An overwhelming majority sitting close to flat, and a scattered minority that gravity has knocked well off that line. There's actually a second, more technically precise way astronomers could define this flat reference plane, called the invariable plane, which passes through the solar system's exact center of mass, angled perpendicular to the system's total angular momentum. In principle, that's the more physically meaningful plane to use. In practice, almost nobody uses it, because it's genuinely difficult to pin down with precision, while the ecliptic is easy to define just by watching the Sun's apparent path across the sky. The trade-off is that the ecliptic drifts very slowly against the fixed background of distant stars over long geological timescales, while the invariable plane, in theory, would not. Astronomers accept that trade-off anyway, because convenience wins out over theoretical purity most of the time, and the ecliptic remains the plane every mission planner, every textbook, and every spacecraft trajectory design actually gets measured against. So that's your answer to the first half of the question. There is a meaningful up and down in the solar system, defined by this flat protoplanetary disk left over from its formation, and every planet orbits close to that same plane because every planet was built from the same flattened sheet of material, spun into shape by the same physics that spins a figure skater faster when her arms come in. Which brings us to the second half, and the part that actually explains the title of this video. If there is a plane, and if up and down mean climbing away from it, why does nothing ever seem to do that? Why, after decades of space exploration, with dozens of missions sent to Mars, to the asteroid belt, to Jupiter, to the icy edges of the solar system, has almost every single one of them stayed close to that same flat disk, instead of just heading straight up and out? The answer isn't that engineers never thought of it. The answer is physics, and specifically a concept called delta V. Delta V is essentially the velocity budget a spacecraft has to work with. Every maneuver it performs, whether that's climbing into orbit, changing altitude, adjusting course, or slowing down to land, spends some of that budget. Once the propellant runs out, the delta V budget is exhausted, and the spacecraft can't change its path anymore, no matter how well its other systems are working. And here's the part that catches a lot of people off guard. Changing your orbital altitude, moving closer to or farther from whatever you're orbiting, is comparatively cheap. Changing your orbital plane, tilting the entire orientation of your orbit relative to where you started, is brutally, punishingly expensive by comparison. The actual math behind it is almost elegant in how unforgiving it is. The delta V required for a pure plane change maneuver comes out to 2 times your current velocity, multiplied by the sine of half the angle you're trying to rotate through. In low Earth orbit, where a satellite is already moving at roughly 7.5 kilometers per second, a plane change of just 60 degrees requires a delta V equal to the entire velocity the spacecraft already has. Run that number through the rocket equation, using a typical chemical engine, and you find that more than 90% of the spacecraft's total mass would need to be propellant just to pull off that single maneuver. Even a modest 1-degree inclination change in low Earth orbit costs around 0.14 kilometers per second of delta V on its own, enough that stacking up a handful of these small corrections can rival the entire delta V spent getting off the ground in the first place. There's a reason this particular maneuver is so punishing, and it comes down to how rockets actually work. The amount of delta V a spacecraft can generate depends on its exhaust velocity, which in turn depends on the type of propulsion system doing the pushing. A cold gas thruster, the simplest kind, has an exhaust velocity equivalent to a specific impulse of only about 70 seconds. A monopropellant system does better, somewhere around 220 seconds. A standard bipropellant chemical rocket, the kind used for most large maneuvers, reaches roughly 320 seconds. Electric propulsion, ion engines and the like, can reach somewhere between 1,000 and 3,000 seconds, dramatically more efficient, but producing only the faintest whisper of thrust in return. Run any of these numbers through the rocket equation, and the relationship isn't linear, it's exponential. A high delta V requirement doesn't just need a little more propellant than a low one. It needs disproportionately, punishingly more, which is exactly why a plane change that would barely register at low speed becomes nearly impossible once a spacecraft is moving at real orbital velocity. This is also why the cheapest way to combine a plane change with anything else is to fold it into a maneuver that's already happening at the slowest point in an orbit. Combine a plane change with the far end of an elliptical transfer orbit, where the spacecraft is moving at its slowest, and the two burns can be blended into one more efficient maneuver, using the combined vector of both changes rather than paying for each one separately. It's still expensive, it's just less catastrophically expensive than trying to rotate a plane while moving at full orbital speed. Launching eastward from a spaceport near the equator helps in a smaller but related way too, letting a rocket reclaim a few hundred meters per second of free velocity from Earth's own rotation, part of why so many major launch sites sit at low latitudes close to the equator in the first place. This is exactly why mission planners almost never try to fix a wrong orbital plane after launch. Instead, they bake the correct plane into the launch itself, choosing a spaceport's latitude and the exact direction, or azimuth, that the rocket flies at liftoff, because propellant spent while still low and slow near the ground goes a lot further than propellant spent trying to muscle a plane change once you're already screaming through orbit at several kilometers per second. Even satellites already parked in geostationary orbit, doing nothing more dramatic than sitting still relative to the Earth below them, still have to spend roughly 50 meters per second of delta V every single year just on station keeping, mostly burning fuel in the north-south direction to fight the Sun and Moon's gravity, which constantly tries to drag their orbital plane out of alignment. Over a 15-year working life, that adds up to around 750 meters per second, a huge slice of a satellite's total fuel budget, spent purely on refusing to drift up or down. Scale that same brutal math up from a satellite circling Earth to a spacecraft trying to escape the entire flat plane of the solar system, and the numbers become almost absurd. The Sun's gravity and the orbital velocities involved at solar system scale are enormous compared to anything in low Earth orbit. Simply pointing a rocket up, away from the ecliptic, and firing the engines is nowhere near enough. You would need an amount of propellant that no rocket ever built, or even seriously proposed, could plausibly carry. It helps to actually know how fast those solar system scale velocities really are, because the numbers aren't the same for every planet, and the differences matter for what comes next. Mercury, tucked in close to the Sun, races along its orbit at about 47.9 kilometers per second. Venus follows at roughly 35 kilometers per second, and Earth, a little farther out, settles into about 29.8 kilometers per second, which is why a full lap around the Sun still only takes us a year. Mars slows to around 24 kilometers per second. Out past the asteroid belt, the pace keeps dropping. Jupiter cruises at only about 13 kilometers per second, Saturn around 9.7, Uranus close to 6.8, and Neptune, the slowest of them all, creeps along at roughly 5.4 kilometers per second. This isn't random. It's Kepler's laws of planetary motion at work. For first worked out by the German astronomer Johannes Kepler in the early 1600s, centuries before anyone understood gravity well enough to explain why the pattern existed. Kepler's third law ties a planet's orbital period to its distance from the Sun, and the practical result is that the farther out a planet sits, the weaker the Sun's gravitational grip on it, and the slower it has to move to stay in a stable orbit. Mercury completes a full year in just 88 Earth days. Neptune takes 165 Earth years to do the same, which means it still hasn't completed a single full orbit since it was first discovered back in 1846. This matters directly for gravity assists, and here's why. A spacecraft borrowing momentum from a planet is really borrowing a slice of that planet's own orbital speed, and Jupiter, despite being the slowest moving of the readily reachable giant planets from Earth's perspective, still carries an enormous amount of momentum simply because it's so unbelievably massive, more than 300 times the mass of Earth, and more than twice the combined mass of every other planet in the solar system put together. That combination, tremendous mass moving at a healthy clip even by outer solar system standards, is exactly what makes Jupiter the single most useful gravitational slingshot available anywhere in the solar system, and exactly why it kept showing up as the key to almost every mission mentioned so far, from Ulysses to Voyager to New Horizons. So if brute force thrust is off the table, how did anything ever manage to climb out of the plane at all? The answer is a trick engineers call a gravity assist, and it's the single loophole that has made every out-of-plane mission in history possible. A gravity assist works by letting a planet do the heavy lifting instead of your engines. As a spacecraft swings past a massive planet, the planet's own gravity bends the spacecraft's path, and because the planet itself is also moving, orbiting the Sun at tremendous speed, a small sliver of that planet's own momentum transfers over to the spacecraft during the encounter. The spacecraft gains velocity and a dramatically altered trajectory, essentially for free, while the planet loses an infinitesimally tiny, genuinely unmeasurable amount of its own momentum in return, because its mass so vastly outweighs the spacecraft's. It's the closest thing space travel has to a genuine shortcut, and it's the only tool ever used to send a human-made object meaningfully out of the ecliptic plane. The first, and still the clearest example of this, is a spacecraft called Ulysses. Ulysses was a joint mission between NASA and the European Space Agency, and its entire purpose was to do something no spacecraft had ever done before: fly over the poles of the Sun. Every previous mission that studied the Sun had done so from somewhere close to the ecliptic plane, essentially staring at its equator. Nobody had ever seen what the Sun's north and south poles actually looked like, because getting a spacecraft into position to look required climbing dramatically out of the flat plane the entire solar system moves through, and as we just went through, that kind of climb is exactly the maneuver that chemical rockets are worst at. The idea for this mission goes back to the early 1970s, when NASA and ESA first began studying what they called an out-of-ecliptic mission, originally imagined as two separate spacecraft, one heading toward the Sun's northern pole, the other toward its southern pole. The mission was formally approved in 1976, its scientific instruments approved the following year, and budget pressure eventually trimmed the ambitious two-spacecraft plan down to a single probe, built by the German company Dornier Systems on ESA's behalf, with NASA contributing the power source, the launch vehicle, and the tracking network needed to stay in contact with it across hundreds of millions of miles. The mission didn't launch on schedule either. It ended up flying 13 years after ESA's Science Council had first given it the green light, considerably delayed by the Challenger disaster, which grounded the Space Shuttle fleet for years and forced a long queue of shuttle-dependent missions, Ulysses among them, to simply wait their turn. That single spacecraft launched on October 6, 1990, riding aboard the Space Shuttle Discovery on mission STS-41 out of Cape Canaveral, Florida. Combined with a two-stage booster and an additional payload module, the shuttle sent this roughly 370-kilogram probe on its way at 11.3 kilometers per second as it left Earth's gravity behind, which at the time made it the fastest interplanetary spacecraft ever launched by anyone. And notice something important there. Even with a gravity assist already built into the plan, this mission still required the combined power of a space shuttle and 3 separate upper-stage rockets just to get the spacecraft moving fast enough to reach its target. That's how much raw energy is involved in even attempting an out-of-plane trajectory, before the gravity assist has done any of its real work yet. Ulysses didn't head toward the Sun first. It headed toward Jupiter, traveling nearly 1 billion kilometers within the ecliptic plane just to get there, arriving roughly 16 months after launch. Jupiter was the target because it's the nearest planet with enough mass to bend a spacecraft's trajectory as dramatically as this mission required. On February 8, 1992, at 12:02 Universal Time, Ulysses made its closest approach to Jupiter, passing about 235,000 miles from the planet, and becoming the 5th spacecraft in history to reach it. Jupiter's gravity did exactly what the mission needed. It flung Ulysses out of the ecliptic entirely, bending its path into an orbit tilted roughly 80 degrees relative to the plane every planet orbits within. From there, Ulysses swung down below the ecliptic, passing over the Sun's southern pole, then curved back up above the ecliptic to pass over the northern pole as well, doing exactly what no spacecraft before it had managed. From roughly the middle of 1993 onward, Ulysses spent an extended stretch of time constantly within the region dominated by the Sun's southern magnetic pole, with its dedicated southern polar observation phase running from June 26 to November 6 of 1994, while flying above 70 degrees of solar latitude. It later swung around to do the same for the northern pole. Originally designed as a 5-year mission, Ulysses ended up operating for 18 years, more than triple its planned lifetime, and along the way, it became one of the most prolific contributors to human understanding of the Sun's activity cycle, the solar wind, and the 3-dimensional structure of the space around our star. Its onboard dust detector also picked up something nobody fully expected going in: a steady stream of genuine interstellar dust, tiny grains that had drifted in from outside the solar system entirely, penetrating deep into the heliosphere. Ulysses monitored that interstellar dust stream continuously, from 1992 all the way through the end of 2007, giving scientists 15 straight years of data on material that had originated somewhere else in the galaxy before ever reaching us. Ulysses proved the concept. A spacecraft could leave the ecliptic plane, but only by borrowing enormous amounts of energy from a planet along the way, never by simply pointing up and firing engines. And it's not the only mission that ended up demonstrating this same hard truth. Even when leaving the plane wasn't the original goal. Not every spacecraft that headed for the outer solar system left the plane though, and the contrast is worth pointing out, because it shows just how deliberate a maneuver like Ulysses's really was. Pioneer 10 launched on March 2, 1972, and Pioneer 11 followed about a year later, on April 5, 1973, both aimed at the outer solar system years before either Voyager left the ground. Pioneer 10 made its closest approach to Jupiter on December 3, 1973, passing about 200,000 kilometers from the planet and becoming the first spacecraft in history to survive a crossing of the asteroid belt and reach Jupiter at all. Pioneer 11 went on to visit Saturn as well. After their respective planetary encounters, both spacecraft were sent onto hyperbolic escape trajectories headed toward opposite sides of the solar system. But here's the key difference. Both of those escape paths stayed close to the ecliptic. Pioneer 10 was tracked at around 67 astronomical units from the Sun, still near that same flat plane, heading almost directly opposite the galactic center. Pioneer 11 ended up on a path inclined only around 15 degrees relative to the ecliptic, heading roughly toward the constellations Aquila and Scutum, a trajectory estimated to bring it near a star in that constellation in about 4 million years. 15 degrees, compared to Ulysses's 80. Nobody engineered the Pioneer missions to leave the plane, because that was never their objective, and their trajectories prove it. Getting dramatically out of the ecliptic doesn't happen as a side effect of any old gravity assist. It has to be the specific goal the entire flyby geometry is built around, the way it was for Ulysses, and only partially, as a byproduct, for the Voyagers. That brings us to Voyager 1 and Voyager 2, the 2 most famous spacecraft ever built, both of which are now, decades after launch, slowly climbing and diving away from the flat plane of the solar system, almost as a side effect of the missions they were actually sent to do. Voyager 1 and Voyager 2 both launched in 1977, sent on what became known as the Grand Tour, a rare planetary alignment that allowed a single mission to visit Jupiter, Saturn, Uranus, and Neptune using a sequence of gravity assists, one planet setting up the next. Both spacecraft crossed the orbit of Mars slightly above the ecliptic plane on purpose, a small early nudge out of the flat disk specifically chosen to steer them clear of the asteroid belt sitting between Mars and Jupiter. Voyager 1 reached Jupiter first, flying past on March 5, 1979, with Voyager 2 following on July 9th of that same year. Then came Saturn, Voyager 1 arriving on November 12, 1980, and Voyager 2 arriving on August 26, 1981. And this is where the two missions genuinely diverged, in a decision that still shapes exactly where both spacecraft are heading right now, in 2026. Mission planners had to choose. Voyager 1 could either continue on toward Titan, Saturn's largest moon, for a close and detailed study of its thick atmosphere, or it could stay on a path that would allow it to continue outward toward Uranus later on. Those two options were mutually exclusive. Getting close enough to Titan meant bending the trajectory in a way that would permanently rule out any future planetary flybys. Scientists chose Titan. That choice sent Voyager 1's path bending sharply northward, up and out of the ecliptic plane, ending its planetary tour for good, but giving it, at the time, the fastest escape velocity of any object humans had ever launched. Voyager 2 took the other path, threading a much more precise trajectory through the Saturn system that let it continue on toward Uranus, and from there, toward Neptune. In doing so, it became the only spacecraft in history to visit all four gas giants in a single mission. It reached Uranus on January 24, 1986, returning the first detailed images and data on that planet, its moons, its magnetic field, and its faint dark rings. Then, on August 25, 1989, Voyager 2 made its closest approach to Neptune, passing less than 5,000 kilometers from the planet's cloud tops. That flyby was deliberately designed to send Voyager 2 over Neptune's North Pole so it could get a close look at Neptune's large, geologically active moon Triton, and that same maneuver bent Voyager 2's trajectory southward, sending it below the ecliptic plane on the course it is still following today. Every one of those flybys, Jupiter, Saturn, Uranus, Neptune, worked the same way Ulysses' single Jupiter flyby worked, stealing a small fraction of each giant planet's own orbital momentum and converting it into spacecraft speed. Stack 4 of those thefts back to back, planet after planet, and by the time Voyager 2 departed Neptune in 1989, it was moving fast enough to escape the Sun's gravity entirely, a feat that would have been essentially impossible using the chemical rocket technology available at the time without this exact chain of gravitational borrowing. Neither spacecraft carried anywhere near enough propellant to achieve that kind of velocity or that kind of trajectory bend on its own. Every degree of tilt they picked up away from the ecliptic came from a planet's gravity doing the work, never from their own engines. So both spacecraft ended up out of the plane, but for opposite reasons and in opposite directions, purely as consequences of the exact flyby geometry each mission needed for its own scientific goals, not because leaving the plane was ever the point. Here's where they stand right now, according to NASA's own current mission data. Voyager 1 is climbing above the ecliptic plane at an angle of about 35 degrees, moving outward at a rate of roughly 520 million kilometers, about 320 million miles, every single year. It's heading in the general direction of the solar apex, which is the direction the entire Sun is moving relative to nearby stars, on a course that will eventually carry it toward the constellation Ophiuchus. Voyager 2 is diving below the ecliptic at an angle of roughly 48 degrees, moving outward at about 470 million kilometers, close to 290 million miles, per year, on a course heading generally toward the constellations Pavo and Indus. Both numbers are worth sitting with for a second. After nearly 50 years of travel, after using every ounce of gravity assist available from 4 different giant planets, the most successful, longest traveling, farthest flung spacecraft humanity has ever built have only managed to tilt 35 and 48 degrees away from the flat plane they started in, not 90 degrees straight up. Not even halfway there for Voyager 1. That's the real scale of how hard it is to leave this plane, even when you've stacked gravity assist on top of gravity assist across an entire grand tour of the outer solar system. There's one more spacecraft worth mentioning here, because it complicates the picture in an interesting way. New Horizons launched on January 19, 2006, leaving Cape Canaveral at about 16.26 kilometers per second, the highest launch velocity ever achieved by a human-made object relative to Earth, fast enough that it passed the Moon's orbit in just 9 hours. Its target was Pluto, and Pluto's orbit, remember, is tilted a full 17 degrees from the ecliptic, the steepest lean of any of the 9 worlds once counted as planets. You might expect that meant New Horizons needed a dramatic climb out of the plane to reach it, the kind of maneuver that sent Ulysses all the way out to 80 degrees. It didn't, and the reason is almost elegant. Pluto's tilted, elongated orbit still crosses back through the ecliptic plane periodically, the same way the Moon's orbit crosses the ecliptic at its nodes. Mission planners simply timed New Horizons' arrival for the exact moment, in July of 2015, when Pluto's own path happened to cross that plane, at a distance of about 32 astronomical units from the Sun. New Horizons did pick up a gravity assist from Jupiter along the way, on February 28, 2007, adding about 4 kilometers per second to its speed, and shaving roughly 3 years off the total trip. But that flyby wasn't built to bend the spacecraft's plane, the way Ulysses' Jupiter flyby was. New Horizons' own orbital inclination sits at only around 2¼ degrees, barely tilted at all, because the mission never needed to fight its way out of the ecliptic. It just needed patience and good timing to catch a steeply tilted world at the one moment it happened to swing back through the flat plane where almost everything else in the solar system already lives. And even at those speeds, hundreds of millions of kilometers covered every year, both Voyagers remain enormously far from anything that could be called the edge of the solar system in every direction. Which brings us to what actually is out there, surrounding all of this flat, disc-shaped activity. Because the ecliptic plane isn't the whole story. It's worth marking exactly how far the Voyagers have actually come, because the numbers put everything else in this video into perspective. Voyager 1 launched first in the mission sequence but second off the pad, lifting off on September 5, 1977, 16 days after Voyager 2, which launched on August 20, 1977, on a slower trajectory that still eventually let it overtake nobody, since Voyager 1's faster path let it reach both Jupiter and Saturn first anyway. Both spacecraft eventually crossed what's called the termination shock, the boundary where the outward-blowing solar wind abruptly slows from supersonic to subsonic speed as it starts pushing against the thin gas of interstellar space. Voyager 1 crossed that shock on December 16, 2004, at a distance of about 94 astronomical units from the Sun. Voyager 2 crossed its own termination shock on August 30, 2007, a bit closer in, at about 83.7 astronomical units, since the shock isn't a perfect sphere and sits closer to the Sun in some directions than others. Beyond the termination shock lies a turbulent buffer zone called the heliosheath, and beyond that lies the heliopause itself, the true outer boundary where the Sun's solar wind finally loses its shoving match against the interstellar medium entirely. Voyager 1 crossed that boundary and entered true interstellar space on August 25, 2012, at roughly 122 astronomical units from the Sun, about 18 to 19 billion kilometers out, becoming the first human-made object in history to leave the heliosphere. Voyager 2 followed on November 5, 2018, crossing into interstellar space at around 119 astronomical units. Both spacecraft are still, technically, considered inside the boundaries of the solar system in the broadest gravitational sense, since the Sun's gravity, and the Oort cloud it's assumed to still be tugging on, extends vastly farther than the heliosphere does. But in terms of the environment directly around them, the plasma, the magnetic fields, the particles, both Voyagers now sit in a region of space shaped far more by the wider galaxy than by our own Sun. Before reaching all the way out to the Oort cloud, though, there's an intermediate region worth understanding on its own terms, because it shows the flat plane pattern starting to fray at the edges, rather than breaking completely. Just beyond Neptune lies the Kuiper Belt, a disc-shaped population of icy bodies that stretches from around Neptune's orbit, roughly 30 astronomical units out, to somewhere past 100 astronomical units. And it isn't one uniform structure, but several overlapping populations, sorted by how they behave gravitationally. The so-called classical Kuiper Belt objects sit on nearly circular, low-eccentricity orbits, mostly between about 39 and 48 astronomical units, largely undisturbed by the giant planets, and their orbits are so consistently flat that the plane defined by these classical objects, for inclinations under about 5 degrees, actually lines up closely with the solar system's own invariable plane, the same theoretical reference plane mentioned earlier. But even within that classical population, astronomers have identified two distinct groups nested on top of each other: a dynamically cold population hugging inclinations below 5 degrees, and a dynamically hot population scattered up past that line, the two groups apparently sharing similar orbital distances but very different histories. Beyond the classical belt sit the resonant objects, locked into orbital rhythms with Neptune, the most famous being the group called the Plutinos, named for Pluto itself, which complete 2 orbits around the Sun for every 3 orbits Neptune makes. And beyond all of that lies the scattered disk, a much more chaotic population, with far larger eccentricities and inclinations, objects still being actively perturbed by close encounters with Neptune's gravity, their orbits stretched out toward aphelion distances that can reach hundreds or even thousands of astronomical units. There's even a term for the sharp cutoff in the classical population past about 48 astronomical units. Astronomers call it the Kuiper Cliff, a sudden drop-off in the number of larger objects that may mark the literal outer edge of the original protoplanetary disk our solar system formed from. So the flat plane doesn't just end abruptly at Neptune's orbit. It thins out gradually, through a belt that's still mostly flat, then a scattered population that's increasingly tilted and stretched, before finally giving way, much farther out, to something that isn't flat at all. There's one more wrinkle worth mentioning here, still unresolved as of this recording. Astronomers studying the most distant, most eccentric Kuiper Belt objects have noticed something strange. A cluster of them share suspiciously similar orbital orientations, physically aligned with each other in a way that shouldn't persist for long on its own, since ordinary gravitational drift would normally scramble that alignment within 100 million years or so. In 2016, astronomers Konstantin Batygin and Mike Brown, the same Mike Brown whose team discovered Eris, Makemake, Sedna, and Haumea, proposed that the simplest explanation is a real, undiscovered planet out there, 5 to 10 times the mass of Earth, orbiting the Sun on an extremely wide, elongated path, its gravity gently herding these distant objects into alignment. They call the hypothesis Planet 9. Nobody has directly observed it. Some researchers argue the apparent clustering is simply an artifact of where telescopes happen to look, rather than real physical alignment, and the debate remains active and unsettled. But it's worth sitting with the shape of the hypothesis itself for a moment, because if a planet like this does exist, it almost certainly isn't sitting anywhere close to the flat ecliptic plane the rest of the solar system respects so closely. Every model built to explain the clustering places its hypothetical orbit tilted well away from that plane, out at a distance so extreme that a single orbit could take somewhere in the range of 10 to 20,000 years to complete. In other words, if Planet 9 is real, it would be the single largest object in the solar system that never got the memo about staying flat, sitting up and out at an angle no gravity assist has ever managed to reach, discovered not by leaving the plane to go look for it, but by noticing its fingerprints on the orbits of smaller, colder worlds scattered around it. Far beyond Neptune, beyond the flat disk of the Kuiper Belt where short-period comets originate, astronomers believe there's a structure that breaks the pattern completely: the Oort Cloud. Unlike the planets, unlike the asteroid belt, unlike the Kuiper Belt, all of which stick closely to that same flat plane we've been talking about this whole time, the Oort Cloud is thought to be a giant spherical shell surrounding the entire solar system in every direction at once, not confined to any plane at all. The idea comes from Dutch astronomer Jan Oort, who proposed it back in 1950 after studying the orbits of long-period comets, the ones that take thousands or even millions of years to complete a single orbit around the Sun. Those comets kept arriving from what looked like essentially random directions in the sky, nothing like the tidy, predictable, flat-plane orbits of short-period comets or planets. Oort worked backward from that pattern and concluded that there had to be a vast, unseen reservoir of icy material surrounding the entire solar system, in every direction, not just within the disk. No telescope has ever directly observed the Oort Cloud. Its existence is inferred entirely from the behavior of the comets that occasionally fall in from it. Estimates place the Oort Cloud somewhere between roughly 2,000 astronomical units from the Sun on its inner edge, out to somewhere between 100,000 and 200,000 astronomical units on its outer edge, depending on which source you're looking at, since nobody has ever measured it directly. Some researchers split it into two regions: an inner, donut-shaped area sometimes called the Hills Cloud, named for physicist Jack Hills, who proposed it in 1981, and an outer region that is genuinely, roughly spherical. And here's the detail that ties this whole video together. The objects that make up the Oort Cloud didn't originate way out there. They formed much closer to the Sun, in the same region where the giant planets themselves were taking shape. As Jupiter, Saturn, Uranus, and Neptune grew, and their gravity swept through the young solar system, countless smaller icy bodies got flung outward by those gravitational encounters. Some were ejected from the solar system entirely. Others ended up in distant, loosely bound orbits that, reshaped slowly over billions of years by the gravity of the wider galaxy, eventually settled into the roughly spherical distribution we now call the Oort Cloud. In other words, the one part of the solar system that genuinely does surround us in every direction, up, down, and everywhere else, only got there because those objects were violently thrown out of the flat plane in the first place, by the same giant planets whose gravity is the only reason Ulysses and the Voyagers ever managed to leave that plane too. The mechanism that built the Oort Cloud and the mechanism that let a handful of human spacecraft tilt away from the ecliptic are, in a real sense, the same mechanism. Even Voyager 1, farther from the Sun than any other human-made object, isn't expected to reach even the inner edge of the Oort Cloud for a very long time still to come, and would take tens of thousands of years to pass through the whole thing, even if it were aimed directly at it, which it isn't. The scale of up and out here isn't measured in years or even centuries. It's measured on a timeline that dwarfs recorded human history many times over. It isn't just spacecraft that reveal how firmly locked to that flat plane most of the solar system really is. The exceptions among the solar system's own natural bodies are just as telling. Pluto's 17-degree tilt already stood out among the 8 true planets, but some of the other dwarf planets discovered out beyond Neptune lean even further. Eris, discovered in January 2005 by a team led by astronomer Mike Brown working at Palomar Observatory, and formerly named after the Greek goddess of strife and discord in September 2006, sits on an orbit tilted about 44 degrees from the ecliptic, more than twice Pluto's lean. Makemake, discovered by that same team in March of 2005 and named in 2008, orbits at an inclination of about 29 degrees. Haumea sits at a similar 28 degrees. Sedna, discovered back in November 2003, leans a more modest 11.9 degrees, but makes up for it with one of the most extreme orbits of any known object in the solar system, swinging from about 76 astronomical units at its closest approach to the Sun out to roughly 937 astronomical units at its farthest, a single lap that takes over 11,000 years to complete. None of these worlds needed an engine or a carefully planned gravity assist to end up tilted this far from the plane. They got there the same way the Oort Cloud got there, through violent, ancient gravitational encounters with the giant planets. Encounters that flung raw material outward and scattered some of it onto orbits that never settled back down flat. The tilted, scattered dwarf planets out past Neptune and the spherical shell of the Oort Cloud even further beyond them are really the same story, told at 2 different distances, both left over from the same chaotic era when Neptune and its neighbors were still rearranging the outer solar system. Now step back even further, past the edge of the solar system entirely, and the same basic pattern repeats itself at a completely different scale. The Milky Way galaxy has its own version of a flat plane, called the galactic plane, and most of the galaxy's 100 billion or so stars, including our own Sun, orbit close to that same flattened structure, for exactly the same underlying reason the solar system is flat: conservation of angular momentum, acting on a much, much larger collapsing cloud of gas, billions of years ago. Our entire solar system orbits the center of the Milky Way at a staggering speed, roughly 230 kilometers per second, which works out to about 828,000 kilometers per hour. Even moving that fast, a single full orbit around the galactic center, sometimes called a galactic year or cosmic year, takes somewhere between 225 and 250 million years, with different scientific sources landing on slightly different precise figures within that range. The Sun sits roughly 8 kiloparsecs from the galactic center, tucked into a minor, partial structure of the Milky Way called the Orion Arm, sandwiched between two much larger structures known as the Sagittarius Arm and the Perseus Arm. And just like the solar system's ecliptic, there's nothing cosmically special about the direction the galactic plane happens to point. It isn't up or down in any universal sense. It's simply the leftover orientation of the specific cloud of gas that happened to collapse and form the Milky Way billions of years ago, spinning in whatever direction it happened to already be spinning when gravity took hold. Other galaxies formed from other clouds, spinning in their own directions, tilted at their own angles relative to ours. For the exact same essentially random reason, our own solar system's disk is tilted the way it is relative to some other star system's disk somewhere else in the galaxy. And that comparison isn't just theoretical either. Astronomers have started measuring the alignment between planetary orbits and stellar spin in other star systems entirely, and plenty of them don't look anything like ours. In our own solar system, every major planet orbits in close alignment with the Sun's own rotation, within just a handful of degrees, and the Sun's equator itself, relative to the invariable plane, is tilted only about 6 degrees. But for a large fraction of the giant, close-orbiting planets known as hot Jupiters, worlds found orbiting other stars in mere days rather than years, the tilt between a planet's orbit and its star's spin axis can be dramatic. Astronomers measure this using something called the Rossiter-McLaughlin effect, watching for a subtle distortion in a star's light as a transiting planet crosses in front of it, which reveals exactly which way the planet is actually moving relative to the star's own spin. One of the most extreme cases on record is a planet called WASP-18b, roughly 10 times the mass of Jupiter, orbiting its star in under 23 hours, so close and so massive that astronomers have observed it, apparently making its own host star behave as though it were far older than it really is. Another well-studied case, a planet called XO3b, was the first exoplanet ever found with a highly inclined orbit relative to its star's equator, a world with about 12 times Jupiter's mass on an unusually eccentric path. One proposed mechanism behind orbits tilted this dramatically is something called the Lidov-Kozai effect, first described by Soviet scientist Mikhail Lidov in 1961 and independently studied by Japanese astronomer Yoshihide Kozai, in which the gravitational pull of a companion star or another massive planet in the same system can slowly warp a planet's orbit over long stretches of time, dragging it further and further from whatever plane it originally formed in. Something like a third of all exoplanets with a measured spin-orbit angle show a misalignment large enough to be considered statistically significant, and in nearly every one of those cases, the tilted planet is a hot Jupiter, so the flat, orderly plane our own solar system settled into was never some universal law that every planetary system has to obey. It's one outcome among several, the quiet, comparatively undisturbed result of a system that mostly avoided the kind of violent gravitational chaos, close stellar companions, planet-on-planet scattering, that leaves so many other systems out there tilted at every imaginable angle. And the pattern doesn't even stop at the edge of the Milky Way. Zoom out past our own galaxy entirely, and astronomers describe something called the supergalactic plane, a much larger flattened structure formed by the arrangement of nearby galaxies bound together in what's known as the local group and the wider structures around it. Similar interactions, similar gravitational sorting over enormous timescales, are thought to have confined most of the stars that make up the Milky Way into its own galactic plane. The same basic process, operating at a scale where individual galaxies, rather than individual planets, are the objects being organized into a flattened sheet. The ecliptic, the galactic plane, and the supergalactic plane are really the same story told 3 times, at 3 wildly different scales, each one just the leftover spin of whatever cloud of material happened to be collapsing at the time. So when you ask why you can never go up out of the solar system, the honest answer stacks up in layers, and every layer tells the same story. On the smallest scale, gravity gives you a personal, local sense of down that only exists because you're standing on a sphere, and it disappears the moment you leave that sphere behind. On the scale of the solar system, up and down exist only because everything, every planet, most of the asteroid belt, formed out of the same flattened protoplanetary disk billions of years ago, spun into shape by the same physics that speeds up a figure skater's spin, and leaving that flat plane costs a staggering, almost prohibitive amount of energy, so much that no chemical rocket has ever attempted it through raw thrust alone. Every single object that has managed to climb meaningfully away from that plane, from the icy bodies flung out to build the Oort Cloud, to the tilted dwarf planets scattered by Neptune, to Ulysses swinging past Jupiter to study the sun's poles, to the Voyagers bending northward and southward during their final planetary flybys, got there by borrowing energy from something else entirely. A planet's gravity, a slingshot, a loophole in the physics rather than a straight shot up. And where a spacecraft didn't need that dramatic a climb, like Pioneer 10 and 11 riding their own hyperbolic escapes almost flat, or New Horizons simply waiting for Pluto's tilted orbit to swing back through the plane on its own, the mission never had to fight the ecliptic at all, because it never needed to. And zoom out past even that, past the solar system entirely, and the exact same flat structure, the exact same story, repeats itself at the scale of the entire galaxy, with our Sun and everything orbiting it swept along inside the Milky Way's own disk, moving at 828,000 kilometers an hour, and still needing somewhere around 230 million years just to complete one single lap. And it isn't even a universal outcome. Plenty of planetary systems around other stars never settled into anything this orderly, tilted instead by close encounters and gravitational tugs into orbits that would make our own tidy, flat solar system look almost improbably lucky by comparison. There is no cosmic ceiling out there, no universal up. There's only the leftover shape of whatever cloud of gas happened to be spinning when gravity decided to pull it together, layer after layer after layer, all the way from the plane you're technically standing on right now, out to the very edge of the observable structure of the galaxy itself. And every time humanity has actually managed to break out of one of those flat layers, even just by a handful of degrees, it hasn't been through brute force. It's been by borrowing gravity from something far bigger than ourselves and letting that do the lifting instead.